Conservation of electric charge. Electric charge is a conserved amount, which means that it cannot be created or destroyed. So you cannot create or destroy an electric charge. Okay, so it cannot be created or destroyed, but it can be transferred from one object to another. So it's like when you say, consider a container that has 1 liter of water. Let's assume that we have 1 liter in this container, and then you put some of this water in another container, so you still have the same one, and you have another container, let's say this one. You fill this one, okay, you fill this one, let's say, with 0.2 liters, so that the remaining amount left in the first one is 0.8 liters. If you add them, 0.8 plus 0.2, it results in 1 liter. So initially we had 1 liter, and then a part was transferred from container 1 to container 2, but the total is still the same. The conservation of electric charges can mathematically be expressed as Q total initial equals Q total final. Assume that we had an object Q1 that had an initial charge, and we have an object 2 that had an initial charge, and then we connect them so that there is a transfer of electrons. Object 1 will end up with Q1 final, its final charge after the transfer, and object 2 will have Q2 final as its final charge. So Q total initial is the total. Q total initial, let's write it there, is equal to Q1 initial plus Q2 initial. Q total final is the sum of the final charges. It is equal to Q1 final plus Q2 final. Let's solve this exercise. Consider two objects of respective charges QA -3 millicoulombs and QB 7 millicoulombs. The two objects are connected together. I will stop at this point and I will start writing the given. I will say I have as a given QA initial and QB initial. How did I know that I'm talking about the initial values? Consider two objects of respective charges QA and QB, and then the two objects are connected by means of a conducting wire. So the -3 millicoulomb for A and the +7 millicoulombs for B, they were given before the connection was made, which means this is the initial condition. So QA initial is -3 millicoulomb and QB initial is +7 millicoulombs. At equilibrium, when we say equilibrium, then we're talking about the transfer of electrons stops. So no more transfer of electrons. The charge on the first object, which is A, was found to be +1 millicoulomb. So QA final is +1 millicoulombs. Calculate the final charge on the other one. So we have to find QB final. It's equal to how much? We apply the mathematical representation of conservation of electric charges. So we have Q total initial is equal to Q total final. Then Q1 initial plus Q2 initial is equal to Q1 final plus Q2 final. Let's replace. We have negative 3 plus 7 is equal to 1 plus Q2 final. So we have 4 is equal to 1 plus Q2 final, then Q2 final is equal to 3 millicoulombs. In part B, calculate the amount of charge transferred. The amount of charge transferred can be calculated by considering one object, which means the charge that is transferred is equal to the difference in an absolute value for A, if we consider object A, Q final A minus QA final minus QA initial. Or if I consider object B, it will be QB final minus QB initial. Let's fix this. So this one was QA final, and this is the absolute value. Let's solve for both to compare to get the answer. So Q transferred is equal to absolute value. We have to go back to the previous slide. QA final is 1 and QA initial is negative 3. So QA final, which is 1, minus QA initial is negative 3. So Q transferred is equal to 4 millicoulombs. Now, if we wanted to solve for B, Q transferred is equal to absolute value. QB final, we found it as 3 and QB initial was 7. So 3 minus 7, and we get 4 millicoulombs. So whether you use it for object A or object B, you should get the same answer. A common mistake that is usually done is that people use Q transferred is equal to QA final minus QB initial. This is wrong. Or they use Q transferred is equal to QB final minus QA initial. This is also wrong. It should be for the same object, either A final minus A initial or B final minus B initial. In the third part, calculate the number of electrons transferred. The number of electrons transferred are directly related to the amount of charge that is transferred. And we know that Q as a charge is equal to the number of particles multiplied by E, which is the charge. So if we were talking about the transferred charge, the number of transferred electrons, and this is E. Okay. Q transferred, we found it as, let's write it transferred, it's not total, so it's transferred. Q transferred, we found it to be 4 millicoulombs. Okay, so let's do this. 4 we will replace in this formula. 4 times 10 to the negative 3, we converted from millicoulombs to coulombs, 10 to the power negative 3, is equal to n into 1.6 times 10 to the power of negative 19 coulombs. So divide both sides by 1.6 times 10 to the power of negative 19. Then n is equal to 2.5 times 10 to the power of 16 electrons. This is the amount of electrons that were transferred. Okay. So let's go back a bit to see. Fine. QA initial was -3 and the QA final was +1. It means that A lost electrons. QB final was 7, QB initial was 7, QB final was 3, which means that B gained electrons. So I can do this. Q transferred for A is 4. It is +4 because it lost electrons. For B, we're using the absolute value, but if I wanted to calculate it, this is the magnitude of the transferred charge. But the polarity is negative because it stands for an amount of electrons that was gained. Another exercise with a different given. Okay, consider two objects of respective charges QA -3 millicoulombs. QA initial is -3 millicoulombs and QB initial is +7 millicoulombs, and the final charge, the relation between the charges, if we read at equilibrium, the charge on the first object and the charge on the second object were related as, we have QB final is equal to 2QA final. Let's see how we solve this exercise. Again, starting with the same rule, electric charge is conserved. Q total initial is equal to Q total final. So Q1 initial plus Q2 initial is equal to Q1 final plus Q2 final. Or we have objects A and B, so we make them A, B, A, B. So QA initial is given as -3. QB initial is +7. QA final is an unknown. And plus we have QB final. QB final is given by this relation. QB final is equal to 2QA final. So instead of a QB final, I can write 2QA final. So -3 plus 7, it results in +4 is equal to 3QA final. Then QA final is equal to 4/3 millicoulombs. And QB final, which is equal to 2QA final, is equal to 2 into 4/3, which results in 8/3 millicoulombs. Okay, the amount of charge transferred, I will do it for one of the objects. I will say let's do it for B. It's the same. Whether I use A or B is going to be the same. So I'll say Q transferred is equal to absolute value of QB final minus QB initial. So Q transferred is equal to absolute value of 8 over 3 minus 7. It results in 4.33 millicoulombs. This is the amount of charge that is transferred. Now, the number of transferred electrons, we will use the same method we used before. Q transferred is equal to the number of transferred electrons multiplied by E as a positive value, because we found Q transferred in an absolute value, so no need to put the minus sign. We have 4.33 times 10 to the power of negative 3 is equal to N transferred into 1.6 times 10 to the power of negative 19 coulombs, dividing both sides by 1.6 times 10 to the power of negative 19, 1.6 10 to the power of negative 19. We get the answer for N transferred is equal to 2.71 times 10 to the power of 16 electrons. So this is the amount of electrons that was transferred from one of the objects to the other one. Exercise 3 about conservation of electric charges with a different concept and a different given. Okay, consider two identical objects. Two identical objects, what does that mean? Identical objects will carry the same final charge. Same final charge at equilibrium, which means that Q1 final is equal to Q2 final, which is equal to Q total initial over 2. Let's see how we will solve this exercise. Consider two identical objects of respective charges, negative 3 millicoulombs and plus 7 millicoulombs. So Q1 initial is equal to negative 3 millicoulombs. Q2 initial is equal to positive 7 millicoulombs. The two objects are connected together by means of a conducting wire. So there's a transfer of electrons. And the system reaches equilibrium. Then the transfer stops. Calculate the final charge on each object. Okay, so from the given, when they set identical, then again we'll say Q1 final is equal to Q2 final is equal to Q total over 2. It's the same. It can be Q total initial or Q total final. We use the same method. So instead of Q total initial, we will replace negative 3 plus positive 7. Okay, so Q total initial is the sum of the initial charges over 2 minus 3 plus 7 results in 4 over 2. It results in 2 millicoulombs. So Q1 final is equal to Q2 final is equal to 2 millicoulombs. So again, whenever the objects are identical, it means that their final charges are equal, and the final charge of each is equal to half of the total initial or half of the total final charge of the whole system. Calculate the amount of charge transferred. So Q transferred is equal to Q1 final minus Q1 initial, or Q2 final minus Q2 initial. So Q transferred is equal to Q1 final is 2 and Q1 initial is negative 3. So 2 minus 3, Q transferred is equal to 5 millicoulombs. This is the amount of charge that is transferred. Calculate the number of electrons transferred the same way as we did before. Q transferred is equal to the number of transferred electrons multiplied by E, and we use E as a positive value. Remember why? Because when we found Q transferred, we used the absolute value. So it was 5 millicoulombs, which means 5 times 10 to the power of negative 3 is equal to N transferred multiplied by 1.6 times 10 to the power of negative 19. Divide both sides. 1.6 10 to the power of negative 19. Okay, so N transferred is equal to 3.125 times 10 to the power of 16 electrons. This is the amount of transferred electrons.